When installing a 120 volts alternating current PLC control panel powered by a UPS, there are several important considerations regarding grounding, safety, and potential problems. Addressing these aspects is crucial to ensure the system's integrity, reliability, and the proper operation of the PLC. Firstly, ensure proper grounding. All components, including the branch circuit, PLC UPS, and metal conduit, must be properly grounded according to National Electrical Code requirements. This ensures a low impedance path for fault currents to dissipate safely, protecting equipment and personnel. Secondly, consider using an isolation transformer for the UPS. This will prevent any possible alternating current leakage from the UPS from entering the main electrical system, reducing the risk of electrical shock and equipment damage. Thirdly, installing a ground rod separately for the UPS can provide a dedicated grounding point for the UPS and isolate it from the building's grounding system. This helps to minimize ground loops and improve the overall grounding effectiveness. Fourthly, providing a separate ground busbar in the PLC control panel will ensure that all PLC components are properly grounded within the panel, further minimizing noise and potential grounding issues. Some obvious potential problems to consider include the potential for ground loops. If the grounding of the UPS, PLC, and metal conduit is not properly coordinated, ground loops can occur, which can introduce noise and interfere with the PLC operation. This can lead to erratic behavior, data corruption, or even system failure. Another potential issue is overcurrent protection. The 15 amps breaker in the PLC control panel may not be sufficient to protect the load if the UPS is oversized. Ensure that the breaker is properly sized to protect the load and the UPS from overcurrent conditions. Electromagnetic interference, or EMI, is another concern. The metal conduit running from the PLC control panel to the GFCI outlet may act as an antenna for EMI, which could disrupt the PLC operation. Shielding the conduit or using alternative wiring methods can help mitigate this issue. Regarding the suitability of this approach for providing clean UPS power, the setup can provide a relatively clean and reliable source of UPS power for the PLC. However, it's essential to address the grounding and safety considerations mentioned above to ensure the system's integrity and the PLC proper operation. To summarize, here are some specific recommendations. Engage a qualified electrician to design and install the system according to National Electrical Code requirements. This will ensure that the system meets all applicable codes and standards and is installed safely and correctly. Consider using a dedicated branch circuit for the UPS to minimize the risk of overloading the 20 amps lighting circuit. This will also help to improve the overall reliability of the system. Shield the metal conduit running from the PLC control panel to the GFCI outlet to mitigate EMI. This can be done by using shielded conduit or by wrapping the conduit with EMI shielding tape. Regularly test the grounding system and inspect all components for proper operation. This will help to identify and correct any potential problems before they cause a failure. To delve deeper into grounding practices, understanding the function of grounding is critical. Grounding, in electrical systems, serves as a vital safety measure. Its primary purpose is to provide a low impedance path for fault currents to flow back to the source, typically the electrical panel. This path facilitates the rapid operation of overcurrent protection devices, such as circuit breakers or fuses, which then interrupt the circuit and prevent electrical shock hazards or equipment damage. The National Electrical Code, or NEC, provides comprehensive guidelines for grounding electrical systems to ensure safety and compliance. Effective grounding relies on several key principles. One of these is the establishment of a low impedance ground path. This means minimizing the resistance and inductance of the path that fault currents must travel. A low impedance path allows fault currents to flow quickly and easily, ensuring that overcurrent protection devices operate promptly. Another principle is bonding. Bonding involves connecting all metal parts of the electrical system together to create an equipotential plane. This ensures that there are no voltage differences between metal parts, reducing the risk of electric shock. Additionally, using a grounding electrode system is vital. This system typically consists of ground rods, ground plates, or underground metallic water pipes that are connected to the grounding system. The grounding electrode system provides a direct connection to the earth, which helps to stabilize the voltage of the electrical system and provide a path for fault currents to dissipate. Grounding requirements outlined in the National Electrical Code, or NEC, are specific and detailed. These requirements cover various aspects of grounding, including the size and type of grounding conductors, the methods for installing grounding electrodes, and the requirements for bonding different parts of the electrical system. For example, National Electrical Code Section 250.24 covers the grounding of alternating current systems. It specifies the requirements for grounding the neutral conductor of the system and for connecting the grounding electrode system. National Electrical Code Section 250.50 outlines the requirements for grounding electrode systems. It specifies the types of grounding electrodes that are permitted and the methods for installing them. National Electrical Code Section 250.118 lists the types of equipment grounding conductors that are permitted for use in electrical systems. These conductors must be sized and installed according to the requirements of the NEC to ensure that they can safely carry fault current. In this specific scenario described, where a 120 volts alternating current branch circuit feeds a PLC control panel with a UPS, several grounding considerations are particularly important. Firstly, the metal conduit that houses the wiring between the lighting panel and the PLC control panel must be properly grounded. This is typically achieved by connecting the conduit to the equipment grounding conductor in the branch circuit. Secondly, the PLC control panel itself must be grounded. This is typically achieved by connecting the panel to the equipment grounding conductor in the branch circuit or to a separate grounding electrode. Thirdly, the UPS must be grounded. This is typically achieved by connecting the UPS to the equipment grounding conductor in the branch circuit or to a separate grounding electrode. If a separate grounding electrode is used for the UPS, it must be bonded to the building's grounding electrode system to ensure that there are no voltage differences between the two systems. Ground loops can be a significant problem in systems with multiple grounding points. A ground loop occurs when there are multiple paths for current to flow between two grounded points. This can create unwanted currents in the grounding system, which can introduce noise and interfere with the operation of sensitive electronic equipment like PLC. To avoid ground loops, it's important to ensure that there is only one path for current to flow between any two grounded points. This can be achieved by using a star grounding configuration where all grounding conductors are connected to a single grounding point. Isolation transformers can also be used to break ground loops by isolating the grounding systems of different pieces of equipment. In addition to grounding, overcurrent protection is another critical safety consideration. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from damage caused by excessive current flow. The size of the overcurrent protection device must be properly matched to the ampacity of the circuit conductors and the rating of the equipment being protected. In the scenario described, the 15 amps breaker in the PLC control panel may not be sufficient to protect the load if the UPS is oversized. If the UPS is capable of supplying more than 15 amps of current, the breaker could trip unnecessarily or, in a worst-case scenario, fail to protect the equipment from damage. To ensure proper overcurrent protection, it's important to calculate the maximum current that the UPS can supply and select a breaker that is properly sized to protect the load. The electromagnetic interference, or EMI, is another potential problem that can affect the operation of PLC. EMI is electrical noise that can be generated by various sources such as power lines, radio transmitters, and electronic equipment. This noise can interfere with the operation of sensitive electronic equipment like PLC, causing them to malfunction or produce inaccurate readings. The metal conduit that runs from the PLC control panel to the GFCI outlet can act as an antenna for EMI, which could disrupt the PLC operation. To mitigate EMI, it's important to use shielded conduit or alternative wiring methods. Shielded conduit is designed to block EMI and prevent it from entering the wiring. Alternative wiring methods, such as using fiber optic cables, can also be used to reduce EMI. In addition to these measures, it's also important to ensure that the PLC control panel is properly shielded and grounded. This will help to minimize the amount of EMI that can enter the panel and interfere with the PLC operation. The suitability of using a UPS to provide clean power to a PLC depends on several factors. One important factor is the type of UPS being used. There are two main types of UPS: firstly, online UPS, and secondly, offline UPS. Online UPS, also known as double conversion UPS, provide the highest level of power quality. They continuously convert the incoming alternating current power to direct current and then back to alternating current, which isolates the load from any power line disturbances. Offline UPS, also known as standby UPS, only switch to battery power when the incoming power fails. This means that the load is not protected from power line disturbances when the incoming power is present. For sensitive electronic equipment like PLC, an online UPS is generally recommended to provide the cleanest and most reliable power. Another important factor is the size of the UPS. The UPS must be sized to provide enough power to support the PLC and any other equipment that is connected to it. It's important to calculate the total power consumption of all the equipment and select a UPS that has a higher capacity. In addition to these factors, it's also important to consider the battery runtime of the UPS. The battery runtime is the amount of time that the UPS can provide power to the load when the incoming power fails. The battery runtime should be sufficient to allow the PLC to shut down safely or to continue operating until the power is restored. When designing and installing a system with a PLC and a UPS, it's always recommended to engage a qualified electrician. A qualified electrician has the knowledge and experience to ensure that the system is designed and installed according to the National Electrical Code and other applicable codes and standards. They can also help to identify and address any potential problems or safety concerns. In addition to engaging a qualified electrician, it's also important to regularly test the grounding system and inspect all components for proper operation. This will help to identify and correct any potential problems before they cause a failure. Regular testing and inspection should include checking the grounding connections, measuring the ground resistance, and inspecting the wiring and components for any signs of damage or wear. By following these recommendations, it's possible to create a safe, reliable, and effective system for providing clean UPS power to a PLC. This will help to ensure the proper operation of the PLC and minimize the risk of downtime or equipment damage. Furthermore, let's explore additional considerations related to grounding, safety, and best practices for PLC and UPS systems. Firstly, surge protection should be implemented. While the described system includes a surge suppressor, it's crucial to ensure that it is properly rated and installed. Surge suppressors protect sensitive electronic equipment from voltage spikes and surges that can damage or destroy components. The surge suppressor should be installed at the point where the power enters the PLC control panel to provide the best protection. Secondly, emergency shutdown procedures should be in place. Develop and document emergency shutdown procedures for the PLC system in case of a power failure, equipment malfunction, or other emergency. These procedures should include steps for safely shutting down the PLC, disconnecting power, and isolating the system. Thirdly, labeling and documentation is paramount. Clearly label all components, wiring, and connections in the PLC control panel to facilitate troubleshooting and maintenance. Maintain accurate documentation of the system, including wiring diagrams, component specifications, and grounding details. This documentation will be invaluable for future maintenance and upgrades. Fourthly, regular maintenance is key. Establish a regular maintenance schedule for the PLC and UPS system. This should include inspecting wiring, checking grounding connections, testing the UPS battery, and cleaning components. Regular maintenance will help to identify and correct any potential problems before they cause a failure. Fifthly, training and awareness are essential. Provide training to personnel who will be operating and maintaining the PLC system. This training should cover the basics of PLC operations, safety procedures, and troubleshooting techniques. Ensuring that personnel are properly trained will help to prevent accidents and ensure the safe and reliable operation of the system. Sixthly, consider harmonic mitigation. UPS systems and other electronic devices can generate harmonics, which are distortions of the alternating current waveform. Harmonics can cause problems with other electrical equipment and can increase energy consumption. To mitigate harmonics, consider using harmonic filters or other harmonic mitigation techniques. Seventhly, power quality monitoring can be beneficial. Consider installing power quality monitoring equipment to monitor the power supplied to the PLC system. This equipment can detect voltage sags, surges, harmonics, and other power quality problems. Monitoring power quality can help to identify and address any potential problems before they cause a failure. Eighthly, remote monitoring and control can improve efficiency. Consider implementing remote monitoring and control capabilities for the PLC system. This will allow you to monitor the system's performance, diagnose problems, and make adjustments remotely. Remote monitoring and control can improve efficiency and reduce downtime. Ninthly, redundancy can enhance reliability. For critical applications, consider implementing redundancy in the PLC and UPS system. This can include using redundant PLC, redundant UPS, or redundant power supplies. Redundancy will ensure that the system continues to operate even if one component fails. Tenthly, consider energy efficiency. When selecting components for the PLC and UPS system, consider energy efficiency. Choose components that are ENERGY STAR certified or that have other energy-saving features. Improving energy efficiency can reduce operating costs and minimize the environmental impact of the system. 11thly, cybersecurity should be addressed. PLC and other industrial control systems are increasingly vulnerable to cyber attacks. To protect the PLC system from cyber attacks, implement appropriate cybersecurity measures such as firewalls, intrusion detection systems, and access controls. In addition to these general considerations, there are also some specific things to keep in mind when working with GFCI outlets in PLC systems. GFCI outlets are designed to protect people from electrical shock by detecting ground faults and interrupting the circuit. However, GFCI outlets can sometimes trip unnecessarily in PLC systems due to noise or other electrical disturbances. To prevent nuisance tripping, it's important to use high-quality GFCI outlets and to ensure that the PLC system is properly grounded. You may also consider using a GFCI outlet with a higher trip threshold or GFCI outlet that is designed for use with electronic equipment. By carefully considering all of these factors, it's possible to design and install a safe, reliable, and efficient PLC and UPS system that meets the specific needs of your application. Remember to always consult with a qualified electrician or electrical engineer to ensure that the system is designed and installed according to all applicable codes and standards. They can also provide valuable insights and recommendations based on their experience and expertise. Moreover, let's further discuss the importance of documentation and record keeping for PLC and UPS systems. Comprehensive documentation is essential for the long-term maintenance, troubleshooting, and modification of these systems. Documentation should include detailed wiring diagrams, schematics, and layouts of the PLC control panel and associated components. These diagrams should clearly show the connections between all devices, including the PLC, UPS, power supplies, input/output modules, and field devices. Component specifications should be included in the documentation, listing the manufacturer, model number, voltage, current, and other relevant parameters for each component in the system. This information is crucial for replacing faulty components or upgrading the system in the future. Grounding details should be meticulously documented, showing the location of all grounding electrodes, the size and type of grounding conductors, and the connections between different grounding points. Proper grounding is critical for safety and to prevent ground loops, so accurate documentation is essential. Software configurations for the PLC and any associated human-machine interfaces should be documented, including program listings, configuration files, and parameter settings. This allows for easy restoration of the system in case of software corruption or hardware failure. Maintenance records should be diligently maintained, documenting all maintenance activities performed on the PLC and UPS systems. This includes the date, time, description of the work performed, and the name of the technician who performed the work. Maintenance records can help to identify trends, predict potential problems, and improve the overall reliability of the system. Troubleshooting logs should be kept to record any problems encountered with the PLC and UPS systems, along with the steps taken to diagnose and resolve the issues. These logs can be invaluable for future troubleshooting efforts and can help to prevent similar problems from occurring. Modification records should be created whenever any changes are made to the PLC or UPS systems, including hardware upgrades, software modifications, or wiring changes. These records should document the details of the changes, the reason for the changes, and the impact of the changes on the system. Regular backups of PLC programs and system configurations should be performed and stored securely. Backups are essential for recovering from software corruption, hardware failure, or cyber attacks. Backup procedures should be clearly documented and followed consistently. Version control should be used for all PLC programs and system configurations. This allows for tracking changes, reverting to previous versions, and comparing different versions of the code. Version control can help to prevent errors and ensure that the correct version of the software is always being used. Security policies and procedures should be documented and followed to protect the PLC and UPS systems from cyber attacks. These policies should include measures for access control, password management, and intrusion detection. Disaster recovery plans should be developed and documented to ensure that the PLC and UPS systems can be quickly restored in the event of a disaster, such as a fire, flood, or earthquake. These plans should include procedures for backing up data, restoring systems, and notifying stakeholders. By maintaining comprehensive documentation and following sound record-keeping practices, you can ensure the long-term reliability, maintainability, and security of your PLC and UPS systems. This will help to minimize downtime, reduce costs, and protect your critical assets. In conclusion, the installation of a 120 volts alternating current PLC control panel powered by a UPS requires careful consideration of grounding, safety, and potential problems. Following the recommendations and best practices outlined will help to ensure the system's integrity, reliability, and the proper operation of the PLC.